Okay, so welcome to another talk for your Civil 473 winter semester of 2022. This is another industry lecture about the application of optimization in consulting work. So if you have not watched the other video, I highly encourage you to go and look at the application of optimization. The other video that I recorded for you, which was about pump scheduling and water distribution systems. There are going to be some concepts in parallel that you would definitely benefit from when you juxtapose these two videos together. In the water systems and sanitary systems, it would be highly beneficial to you. So today we're going to talk about sanitary collection networks and how the application of optimization in these systems. We're going to look at how we can optimize the calibration of sanitary collection networks during a wet weather event. So this was a part of a real case study, or like a longer study master plan that we did for an Ontario client. And as a part of this master plan, we developed the model and then we calibrated the model. Now, if you've ever attended any of my previous talks, for example, I gave a talk last year and the year before about principles of hydraulic modeling for engineering students and young professionals at Queen's University. I talked about how we developed the models and how these models should be calibrated in order to be more realistic and more informative. So, my name is Saeed Hashemi, and I am very happy to be here for another talk with you on calibration, and I'm from Jacobs Engineering in Toronto. So, with that, I trust that you've already watched the previous video that I provided for you, and you're already familiar with my field of work. Now, let's go into what we have today. An introduction about model calibration. So, what is model calibration? The gist of calibration is to minimize the difference between observed data and model results, meaning that when a model is developed or digitized, it is not going to be very useful until it's calibrated, because necessarily the model, if it's a water distribution or wastewater collection model or any other kind of model that you can imagine, if it's not calibrated, it's not going to show you realistic results. So how are we going to get a model calibrated? In this case, which is sanitary collection system, we're going to go out in the field and install pressure flow monitors and collect the data and then process the data and tweak the model parameters in order to minimize the difference between the model results and the data collected out in the field. Sometimes also, the parameters that we're trying to calibrate the model for could be slightly contradictory. For example, if we want to calibrate for model peak flows, volumes, or flow depths across the system, not all the time these three would go hand in hand. Also, we want to be able to calibrate for multiple rainfall events. Now we're going to talk about rainfall events and wet weather calibration in a second. And also, we're monitoring flows in different locations for different rainfall events. So that is going to get things a little bit complicated because we would have to tweak some parameters to perform optimally in different locations and in different times. So now, as a matter of fact, I've done this before in consulting manually, and it's quite time-consuming and frustrating because it's basically trial and error, and it usually becomes the critical path in modeling projects. So what we did in here was optimization, or first automation and then optimization of calibration, which is fast, efficient. You're going to get the model calibrated in a matter of hours. Yes, you heard that right, in a matter of hours, instead of probably weeks, as I have experienced in even small models. And it's a significant reduction in labor hours from a project management point of view. So that's why we use optimization of calibration, or automation of calibration. So if you'll remember from my other talk about application of optimization in water distribution systems and sanitary, when compared to this session, which is mainly about sanitary, there is a surprising fact that software packages like WaterGems and InfoWater, they already have optimization toolboxes in them for calibration, for any other kind of like design optimization or operational optimization. But it's strange that we don't have this luxury when it comes to wastewater modeling. For example, InfoWorks does not include anything like that, or SewerGems or PC Swim, which is the case that the software that we developed this specific case study or model in. So now, our novelty was not only to use optimization, but to use some sort of artificial intelligence, or AI, in order to expedite that kind of traditional optimization. Now, I am a traditional optimization person, and usually for me, it is nice to model or simulate tens of thousands of iterations in order to find an optimal solution. But here, we ended up using RSC, which is Response Surface Characterization, which is going to look at a mathematical relationship between the inputs and outputs of each iteration of optimization, and that is going to expedite finding optimal solutions. So that was one thing that was added into the whole traditional optimization, if you will. The other novelty is when it comes to sanitary flow monitoring. If you look at the diagram on the right-hand side, you can see the differences between order 1s, order 2s, order 3s, and 4s. So what's happening in here is order 1 in blue is anything that wouldn't have any other flow monitors upstream of them. Order 2 in green, you can see there is order 1 upstream of order 2. And in terms of, the system branching together and developing, going downstream, order 3 would have order 1 and 2 upstream. And order 4, in this case shown in red, is downstream of order 1 and then 2 and then 3. So what we ended up using or suggesting in here as another layer of efficacy or efficiency, if you will, was to order group, meaning that all the order 1 meters were optimized or calibrated simultaneously, and then all the order 2s, and then all the order 3s, and independently. So the number of model simulations significantly improved, meaning that the number decreased in a very interesting fashion. So now, if you're wondering, for each order, we end up having only 30 runs, which is quite fascinating, as opposed to a traditional optimization run that would require at least tens of thousands of different simulations. So now, here's the gist of calibration if you want to look at it visually. So before calibration, on the left-hand side, you can see modeled is solid black line, and observed data would be dashed lines in blue. There's quite a huge discrepancy. And on the right-hand side, after calibration, tweaking the model parameters, you can see that there's a great fit between the modeled and observed data. So now, this is not the result for this very specific case study, but this is basically a summary of what we're after as a result of using auto-calibration or optimized calibration in this case. So now, what is wet weather? In sanitary collection systems, there are 3 different types of flow in the sanitary sewers. The first is GWI, which is shown in orangish yellow, which is groundwater infiltration. That part of the flow is always in there, and no matter what kind of weather we're getting, if it's dry or if it's wet, any kind of extreme weather, we're going to have a constant flow coming into the pipes through the cracks and fissures, known as groundwater infiltration. Now, the other one that is shown in brownish red, BWF, that is basically the flow that is the result of human activities, which is patterned throughout the day with a diurnal pattern. That is produced by the residents in the residential area. So that is your actual sanitary flow. And there is another blue part, RDII, or rain-driven infiltration and inflow. That you can see there is a correlation with that rainfall coming from the top, which is precipitation. So when there is a precipitation, there is going to be a rain-driven response in the sanitary system as well. We're not supposed to see that ideally and theoretically, because the sanitary collection system, if it's not combined, especially if it's not combined, we shouldn't see any sort of response as a result of precipitation. But in reality, we do see that kind of precipitation response, which is called RDII. Now, that RDII, the blue part, that is going to be the blue solid line on the right-hand side also, is mimicked or simulated by 3 sets of RTK parameters. Okay, the first set of RTK values would be the first unit hydrograph, which is the short-term response. The second set of unit hydrograph, the second set of RTK values would represent a hydrograph for medium-term response, and the last set of RTKs would be for long-term. So, in order to simulate each manhole's response, we would need to calibrate basically 9 different parameters: R1, R2, R3, T1, T2, T3, and K1, K2, K3. So there are 9 parameters. It's really hard to calibrate and tweak them in order to get that basically blue curve or blue hydrograph of the rainfall. So that's why we're using this automated or optimized calibration, so that we can try different values of RTK in order to basically simulate a real rainfall event in each and every single subcatchment area that we're doing the flow monitoring for. So now, R is basically the response. T in each case, in each of the 3 cases, would be time to peak, and K is the time to recess. So that's how we mimic that kind of real overall hydrograph with the 3 unit hydrographs. Now, the people that were involved in this study, I'm not going to take the whole credit for myself. It was a bigger group of people, but the main people are basically myself. As you might have seen my other talk. If not, I highly encourage you to go back and look in there if you want to familiarize yourself with my work and what I've been doing, mainly as an energy and operation person in water distribution systems. I've been working on that kind of area for long years now. But in consulting, I've been working on water and sanitary and stormwater models, master planning, calibration, optimization, or any sort of a transient analysis, if you will. That's my background. Our main modeler, who was in charge of programming this whole awesome idea, John Myers of our Cincinnati office, he is basically the brain box behind this, and I was liaising between his work and the client expectations. And our project manager and senior hydraulic modeler, Andrew Long from our Toronto office, he was basically supervising this whole work, and we managed to use this amazing tool developed by John Myers in this real case study that you're about to know more on. So, the highlight of my previous work, as I've mentioned before, could be found in different journals, as I have summarized in here, and different conferences. But this very specific topic was presented early March 2022 at a conference by CHI, which is the developer of PC Swim software, called ICWMM Conference 2022. And you can also find the YouTube video for it. As I presented, they recorded this video about this optimized calibration. If you're interested in it, definitely I encourage you to go and find and take a look at it. So, now the case study, the real case study that we used, City of Clarence, Rockland. You can see, if you follow the cursor around here, this is the capital of the nation, Ottawa, and this is City of Clarence, Rockland, and here's a closer view or zoom on the right hand side. Here's the model in PC Swim. You can see the urban forms and what the model looks like, and where the flows come and go. It serves a population of around 15,000, give or take. There is one treatment plant beside the Ottawa River, 9 pump stations existing, and there's going to be more as we explored during the master plan based on the population growth and projection in the years to come. Number of pipes, 959, and number of manholes, 918, just for you to have an idea of how big the model is, which is not a big model, it's a medium-sized model. Now, this is the very same system, the real GIS representation of the model that we used for our flow monitoring plan. So any of those red triangles represents the flow monitoring locations that we install flow monitors in order to collect the data. So here you can see there are 9 locations, but because of the data quality, this location, Laurier Street, we ended up putting away because of the turbulence. So here's a point for you. You got to choose strategically, make sure that based on the system configuration, you're not going to get bad data quality because of potential turbulence. And also, you want to cover the whole system so that each sewer shed or subcatchment that is going to a pump station could be monitored completely and could be calibrated. So for each flow monitoring location in here, we develop RTK for short-term response, medium-term response, and long-term response. For each of these flow monitoring locations, again, I know I'm repeating myself, we're going to calibrate 9 RTK parameters. So here are the results, but we were trying to calibrate the model in order to meet 2 different criteria: peak flows for during a wet weather event to be between -15% and +25%, and average flows between -10% and +20%. So there is a little bit of a maneuver room, as we can't really calibrate to 100% of flow accuracy. Here is the summary that we've gotten from Peel Region Modeling Guideline. You can see this is the summary of it, and this is what we try to achieve throughout this whole calibration practice. Now, let's go take a look at the results, and you can see for the 8 different locations out of 9, because one of the locations provided bad data quality, we have RTK for short term, medium term, and long term. Now, you can see the values look kind of random because throughout the whole optimization procedure, these values are changed. Different values are tested through trial and error to get the best results. So you can see in some of the sewer sheds or flow monitoring areas like Caron or Easement or Saint Jacques Street or Chamberlain, there are different R values, T values, and K values for short term, medium term, and long term. So these are basically the optimized values for RTK. Now, I'm going to show you some more in-depth comparison of peak flows and mean, or in other words, average flows. You can see for this Caron Street location, out of the 2 events, I'm showing the better one, which is event number 1. You can see that the blue line versus the white line, which is the observed, how they're comparing. As summarized down below, the peak values are only 2.3% off, and the average values are 0.8%, which is pretty good compared to 15 to 25% or -10 to +20%. So that's quite a success. The other thing, the other location is the Easement that we're looking at, another of those flow monitoring locations, and you can see the peak value is -10%, which could go down to -15%, so we're good. We're between -15% and +25%, and the average value is only 3.4% more than the observed. So this is quite another successful example. I'm going to go over to the next location, but you can see there's a little bit of time difference between the peaks happening together. In this case, we were not very concerned about the time difference, but that is something that we could certainly work on, because no work is 100% perfect. There's always room for improvement, and that could be also minimized or added as an optimization objective to the program to reduce the time between the observed peak and the model peak. The next one is Saint Jacques Street. In this case, you can see the maximum flows are quite close to each other, only 0.33%, and the average flow only 3% different. Very successful and good kind of calibration, apart from the fact that there's a time difference between the 2 peaks of observed, being the yellow line, and the model being the darker line. Chamberlain Street, again, apart from a little bit of time difference, there's a very good correlation, or there's a very good match between the peak flows, which is almost bang on, and the average flows. That would be 5% lower than the observed, which is quite good. Albert Street was downstream of another pump station. This is a good example of that order too. As you can see, spikes coming down from another pump station upstream. That is impacting the data quality, but you can see still the peak flows are very close, only 0.64%, which is not even 1%, and the average values are 2.77, or if we round it down, 3% lower than the average flows observed. So, in order to conclude, we used same order of flow monitors to simultaneously optimize independently to save some time and increase the accuracy. We can also prioritize some of the rainfall events. So we need to extend out when we're collecting the data out in the field. We want to make sure that we're going to collect the data long enough, 2 months, 3 months. In this case, we flow monitored for 3 months to be able to capture some of the extreme events, being dry, and being wet as a result of any sort of rainfall, so that we can calibrate for those extreme events. And if you have multiple significant rainfalls, then you can prioritize the better events if you want when you're looking at your data compared to some other events that you have recorded. We're also working on this framework that John has developed, so that we can also use it for other kind of optimization in these systems using EPA SWIM, InfoWorks ICM, and HMS models. So we realize that this could be a very huge time saver and budget saver when it comes to any sort of consulting project, apart from being an interesting academic and research idea. So just like any other time, if you have any questions, because this is a recording and we don't have the chance to interact and have some sort of Q&A session, collect your questions. If you want to stay in touch, you can find me on LinkedIn, or you can flip your questions to Dr. Paez, and then I will know about your questions and we can find a way to answer your questions. Thank you very much for your time, and I hope that these slides have been informative to you.